In the digital world, we've built everything. Everything comes down to a simple on or off, a 1 or 0. So how in the world do we get from that super basic idea to the incredibly complex tech we hold in our hands every day? Well, the answer is in the art of making the complicated simple. Let's get into it. Okay, take a look at this. This is a Boolean equation. It looks intimidating, I know, but it's really just a sentence that describes how a digital circuit is wired up. Each part represents a tiny building block called a logic gate. So yeah, this equation describes a pretty big, complex circuit. This is our starting point.
Now, what if I told you that that entire, long, complicated mess of an equation is functionally the exact same as this? S equals C. Yep, all that complexity, all those gates and wires can be boiled down to just a single input, from a tangled web to pure, simple elegance.
So this is the big question, right? How is that even possible? It feels like some kind of magic trick, but I promise you, it's not magic. It's logic. And we're about to pull back the curtain and see exactly how it's done.
First things first. Before we can simplify anything, we have to know exactly what our circuit is supposed to do, for every single possibility. And for that, we need our first tool, the truth table.
You can think of a truth table as the ultimate instruction manual for a circuit. It doesn't care how the circuit works, just what it does. It meticulously lists every possible combination of inputs, all the A's, B's, and C's, and tells you the one correct output for each case. It's our rock-solid source of truth.
Let's look at a super simple example. The function here is A and B. The table shows you clear as day that the output is only 1 when both A and B are 1. For every other combination, the output is 0. No ambiguity, no guessing. It's all just mapped out.
All right, so now that we have our source of truth, it's time to meet the real hero of our story. This is the clever visual tool that lets us see the shortcuts hidden deep inside the logic. Meet the Carnot map.
So a Carnot map, or a K-map for short, is really just a truth table that's been taken apart and put back together in a special way. It's a grid, and its unique layout is designed to do one thing absolutely brilliantly: make simplification patterns literally jump off the page.
And this shows that transformation perfectly. On the left, you've got your standard, boring truth table. On the right, that exact same information is plotted onto a K-map. See? Each little box in the grid corresponds to a row in the table. It's the same data, just organized into a new, much more powerful shape.
Okay, so we've got this new grid shape. How does that help us? Well, this is where the magic really happens. The secret to simplifying with a K-map isn't about doing a bunch of complicated math. It's about a simple visual trick: grouping.
All right, let's look at a new problem, already plotted on a K-map for us. We've got two 1s here. These are the two situations where our circuit's output should be on. Right now, this looks like two completely separate things, two separate terms in our equation, but they have a special relationship.
And that relationship is that they're neighbors. In the world of K-maps, neighbors are just cells that are right next to each other, horizontally or vertically. And here's the crucial part. Neighbors always differ by only one single input variable. Everything else about their coordinates is exactly the same.
So what do? We draw a loop around these two neighbors. Now let's look closely at what's happening inside this group. As we move from the cell on the left to the one on the right, what's changing? Well, the value of A, it stays constant. It's always 1. But look at B. It flips from a 0 to a 1.
And this leads us to the single most important rule of the K-map. Any variable that changes inside a group is irrelevant. It doesn't matter. We can just eliminate it. So B disappears. It's gone. So what are we left with? Just the one variable that stayed the same, A. Our whole equation just simplified down to y equals A. That's the trick.
This whole grouping thing is incredibly powerful. But believe it or not, it gets even better. There are a couple of, let's call them pro moves, that let us find even more ways to simplify.
Okay, first you have to stop thinking of the map as a flat square. Imagine you can roll it up into a tube. The left edge and the right edge are actually touching each other. That means a cell on the far left can be neighbors with a cell on the far right. The same is true for the top and bottom. This wraparound trick lets us form groups we might have missed otherwise.
The second trick involves these things called don't cares. And these are basically the wild cards in our logic puzzle. They give us the flexibility to make our groups as big as possible. And remember, bigger groups always means simpler equations.
So what on earth is a don't care? Well, it's an output for an input that is physically impossible. Think about it. Say you're designing a circuit for an electronic device. It's only ever going to show the numbers 1 through 6. The input combinations that would mean show a 0 or show a 7, they're never ever going to happen. So we literally don't care what the output is in those cases. We mark it with an X.
Now check this out. Here's a K-map where we have a couple of 1s that we need to group. We could just make a small group with those 2 1s, but notice those X's, our don't cares, sitting right nearby? They're an opportunity.
We can just decide to treat those X's as if they were 1s, but only if it helps us make a bigger group. And by including them, we can suddenly form a group of 4 instead of just 2. That larger group eliminates way more variables, and that gives us an even simpler final circuit. We're using the wildcards to our advantage.
Look, this has been a really fascinating puzzle for sure, but it's so much more than just a mental exercise. This whole process of logic minimization is absolutely fundamental to the technology that powers our entire world.
Every single time we eliminate a logic gate, we save real physical space on a silicon chip. That means we can make smaller, cheaper chips. It means less power gets used, which leads to longer battery life. And you know what? Simpler circuits are also faster circuits. This isn't just theory. It directly impacts the cost, the performance, and the efficiency of every single electronic device you own. Of course, for the crazy complex chips in today's world, with millions or billions of components, engineers aren't drawing these maps out by hand. No way. They have incredibly sophisticated software that uses advanced algorithms to do this exact same process, but on a massive scale, optimizing circuits with thousands of variables in the blink of an eye. So we've seen how a really simple visual trick, just rearranging a table into a grid, was one of the keys that unlocked the digital age. It allowed engineers to design complex things efficiently. But it kind of leaves you with a big question, doesn't it? What are those powerful algorithms that took this idea to the next level? And how do they possibly tackle the mind-boggling complexity of today's technology? Well, that's a story for another time.